we're going to talk about molecular or formula mass. So if we were given the molecular formula of any compound and we wanted to find the molecular or formula mass of that compound, this is what we do. Step 1, dissect the compound into its respective elements. 2, look up each element's mass on the periodic table. Step 3, multiply each element's mass by the amount of that element in the compound. And step 4, which is the last step, we add. So let's look at an example and see how this is all done. If we were given C3H7Br, step 1, dissect the compound into its respective elements. Okay, in C3H7Br, we have C, H, and Br. That's step 1. Step 2, look up each element's mass on the periodic table. So if we pull out our periodic table and we look up C, we find that C has a mass of 12.011. For H, we find 1.008. And for Br, we find 79.904. Multiply each element's mass by the amount of that element in the compound. For C, we have 3 C's, so we multiply 12.011 times 3. For H, we have 7 H's, so we multiply 1.008 by 7. And for Br, we only have 1, so we multiply 79.904 times 1. We then multiply these all out. 12.011 times 3 is 36.033. 1.008 times 7 is 7.056. And 79.904 times 1 is still 79.904. Finally, we're going to add these numbers up. So we add 36.033 plus 7.056 and 79.904. Adding those together, we get 122.993. And this is the molecular or formula mass of C3H7Br. Let's try another example. MgHCO3 2. Step 1, dissect the compound into its respective elements. Mg, H, C, and O. Step 2, look up each element's mass on the periodic table. So we pull out our periodic table and we look up Mg and we find 24.305 for Mg, 1.008 for H, 12.011 for C, and 15.999 for O. Next, multiply each element's mass by the amount of that element in the compound. For Mg, we're going to multiply by 1 because there's only 1 Mg in the compound. For H, we're going to multiply by 2. Why are we going to multiply by 2? We multiply by 2 because we have HCO3, but the parentheses around HCO3 tells us that we have 2 HCO3s. So since we have 2 HCO3s, we have 2 hydrogens. So we multiply by 2. For carbon, we're also going to multiply by 2 for the same reason. In one HCO3, there's 1 carbon, but in this compound, we have 2 HCO3s. And finally, for oxygen, we're going to multiply by 6. Again, for the same reason. In one HCO3, we have 3 oxygens, but in 2 HCO3s, we have 6 oxygens. So we're going to multiply oxygen by 6. We're going to multiply all these out. And finally, add them all up. 24.305 plus 2.016 plus 24.022 plus 95.994 is equal to 146.337. And this is our final molecular mass or formula mass of MgHCO3 Next, we're going to talk about converting the mass of an element or compound to moles of that same element or compound. The key here is divide the given mass in grams by the molar or formula mass, which we just talked about calculating. So it's very important to remember, whenever you're going from mass to moles, you divide the given mass in grams by the molar or formula mass. Let's look at an example. Calculate the amount in moles of 647 grams of BaOH2. Step 1. Convert mass to grams. We already have 647 grams in grams, so we don't need to do anything for this step. Step 2. Find the molar mass of the element or compound. The molar mass of BaOH2 is 171.341 grams per mole. I did this by finding the atomic mass of Ba, finding the atomic mass of O, and finding the atomic mass of hydrogen, multiplying those masses by the amount of each element in the compound, adding them up like we just talked about to get 171.341 grams per mole. And we use this grams per mole units for molar mass. We're going to see this all the time. The units for molar mass is always grams per mole. Step 3. Divide the given mass in grams by the molar mass. So we're going to take 647 grams and divide it by our molar mass, 171.341 grams per mole, and we get 3.776 moles of BaOH2. So we take our given mass in grams and divide it by our molar mass, which we calculate. And that gives us our moles of BaOH2. Let's try another example. Calculate the amount in moles of 218 milligrams of CH3CH2SH. Step 1. Convert the mass to grams. Now here we're given 218 milligrams, which is not in grams. So the first thing we have to do is convert 218 milligrams to grams. We do this by dividing by 1,000. 218 milligrams is equal to 0.218 grams. Step 2. Find the molar mass of the element or compound. And I did that here. The molar mass of CH3CH2SH is 62.136 grams per mole. And like I said, I did this exactly the same way we were doing it before. I dissected the compound into C, H, and S. I found the molar mass of C, H, and S, and I multiplied each one by the respective amounts in the compound. And I got a molar mass of 62.136 grams per mole. Step 3, divide the given mass in grams by the molar mass. So we're going to divide our mass in grams, which is 0.218, by 62.136 grams per mole. Our given mass in grams divided by our molar mass. And we get 0.004 moles of CH3CH2SH. Now we're going to talk about the reverse of this process, converting the moles of an element or compound to mass of that same element or compound. The key here is to now multiply the given moles by the molar or formula mass. Important to remember, going from moles to mass, we multiply the given moles by the molar or formula mass, which we should be experienced with calculating by now. Calculate the mass in grams of 0.773 moles of KOH. Step 1. Convert the given to moles. But this step is usually not needed. I included this step because sometimes we might be given millimoles, which we'll see in a bit. But usually we'll be given moles. If that's the case, we don't need to do anything. So in this case, 0.773 moles is given. We don't need to do anything. Step 2, find the molar mass of the element or compound. So I'm going to find the molar mass of KOH just the same way as we've been doing it before, and I get a molar mass of 56.105 grams per mole. Step 3, multiply the given amount of moles by the molar mass. So I'm going to multiply 0.773 moles times 56.105 grams per mole, which is our molar mass, which we've calculated, and we get 43.369 grams of KOH. This method is always going to give you an answer in grams. If you multiply moles times grams per mole, you end up with grams always. Calculate the mass in grams of 0.391 millimole of CH3,3SI. Step 1. Convert the given to moles. Usually not needed, but in this case, since we have 0.391 millimoles, we have to convert millimoles to moles. And we do this by dividing by 1,000 again. 0.391 divided by 1,000 is 0.000391 moles. Step 2, find the molar mass of the element or compound. So I'm going to find the molar mass of CH3,3SI, and I get a molar mass of 73.191 grams per mole. Step 3, multiply the given amount of moles by the molar mass. So we're going to multiply our given moles, which is now 0.000391 moles, times 73.191 grams per mole, and we get 0.029 grams of CH3,3SI. Next, we're going to talk about going from moles to numbers of atoms or molecules. Converting the moles of an element or compound to amount of atoms or molecules of that same element or compound. The key here is to multiply the given moles of element or compound by Avogadro's number. Avogadro's number is a constant number. It's a number that you should be very familiar with. You should memorize it. Avogadro's number is equal to 6.022 times 10 to the 23rd. Calculate the number of molecules in 4.68 moles of H2S. Step 1. Convert the given to moles. We're given 4.68 moles, so we don't need to do anything. We're already in moles. Step 2. Multiply the amount of moles by Avogadro's number. So we're going to multiply 4.68 moles times 6.022 times 10 to the 23rd, which is Avogadro's number, always. So we multiply 4.68 times 6.022 times 10 to the 23rd, and we get 2.818 times 10 to the 24th molecules of H2S. Let's try another example. Calculate the number of molecules in 58 grams of H2S. Step 1. Convert the given to moles. Now, as we can see from the problem, we're given 58 grams of H2S. So we must convert 58 grams to moles of H2S. 58 grams of H2S to moles of H2S. We've talked about converting mass of an element to moles of an element by dividing the mass of the given mass of the compound by its molar mass. So we're going to divide 58 grams divided by the molar mass of H2S, which is 34.082 grams per mole, and we get 1.702 moles of H2S. So I'm just taking the given grams, dividing by the formula or molar mass of H2S, which I've calculated to be 34.082 grams per mole, and we get 1.702 moles of H2S. 2. Multiply the amount of moles by Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. So we multiply 1.702 times 6.022 times 10 to the 23rd, and we get 1.025 times 10 to the 24th molecules of H2S. Next, we're going to talk about stoichiometric relationships. If I had one molecule of a hypothetical compound A2B, so a hypothetical compound that has 2 atoms of A and 1 atom of B to make one molecule. This molecule contains 2 atoms of A and 1 atom of B. So one molecule of A2B contains 2 atoms of A and 1 atom of B. Pretty simple. Let's say we have another hypothetical compound. We have one molecule of X2Y5. In one molecule of X2Y5, we have 2 atoms of X and 5 atoms of Y. We know this because we can see in the subscripts we have 5Y and 2X. So in one molecule of X2Y5, we have 2 atoms of X and 5 atoms of Y. Let's go back to our one molecule of A2B. We said in one molecule of A2B, we have 2 atoms of A and 1 atom of B. What if we now change this to 2 molecules of A2B? How many atoms of A do we have now, and how many atoms of B do we have now in 2 molecules of A2B? In 2 molecules of A2B, we have 4 atoms of A and 2 atoms of B. Why is that? In one molecule of A2B, we had 2 atoms of A, which means in 2 molecules of A2B, we have 4 atoms of A, because we now have double the amount of molecules, which means we have double the amount of atoms of A. The same thing goes for 2 atoms of B. Why do we have 2 atoms of B now? We have 2 atoms of B because we had 1 atom of B in one molecule of A2B. Since we've now doubled the amount of A2B, we have double the amount of atoms of B. We've multiplied the amount of atoms of B by 2, because now we have 2 molecules of A2B. What if we had 4 molecules of X2Y5? How many of each atom do we have now? We said that in one molecule of X2Y5, we had 2 atoms of X and 5 atoms of Y. So in 4 molecules of X2Y5, we have 8 atoms of X, because we now have 4 times the amount of X atoms. And we have 20 atoms of Y, because we now have 4 times the amount of Y atoms, because we have 4 times the amount of molecules. We multiply everything times 4. Let's change this to moles. If we are dealing with moles, it is the same concept as molecules. If we have 1 mole of A2B molecules, we have 2 moles of A atoms and 1 mole of B atoms, because the subscripts in the molecular formula tells us how many atoms of A per molecule. It also tells us how many moles of A atoms per mole of A2B molecules. So we have 2 moles of A atoms and 1 mole of A2B molecules, and we have 1 mole of B atoms and 1 mole of A2B molecules. Just because we have 1 atom of B per 1 A2B molecule. 1 mole is just scaling this up to many molecules. 1 mole makes 2 moles of A atoms and 1 mole of B atoms. What if we had 2 moles of X2Y5 molecules? In 2 moles of X2Y5 molecules, we have 4 moles of X atoms and 10 moles of Y atoms. Why? in 1 mole of X2Y5 molecules, we would have 2 moles of X atoms and 5 moles of Y atoms. But since we have 2 moles of X2Y5 molecules, we multiply everything by 2. So we now have 4 moles of X atoms and 10 moles of Y atoms. 2 times 2 is 4 for X atoms, and 2 times 5 is 10 moles of Y atoms. An example question that we might see is, how many moles of each type of element are present in 0.25 moles of CrCl2 NH3,4Cl? So we have 0.25 moles of this complicated compound. How many moles of Cr atoms are present in this compound? We multiply 0.25 moles of the compound times 1 mole of Cr atoms per mole of the compound. There is 1 atom of Cr in the compound, therefore there is 1 mole of Cr atoms per mole of the compound. How many moles of Cl atoms do we have? We multiply 0.25 moles of the compound times 3 moles of Cl per mole of the compound. There are 3 Cl atoms in the compound, therefore there are 3 moles of Cl per mole of the compound. For N, multiply 0.25 moles times 4 moles of N per mole of the compound. There are 4 atoms of N per molecule, therefore there are 4 moles of N atoms per mole of the compound. And again for H, 0.25 moles times 12 moles of H per mole of the compound. There are 12 atoms of H per 1 molecule of the compound, therefore there are 12 moles of H atoms per mole of the compound. Multiplying these out, we get 0.25 moles of Cr, 0.25 moles times 3, or 0.75 moles of Cl, 0.25 moles times 4 moles of N, 1 mole of N, and 0.25 times 12 moles of H, 3 moles of H. So altogether, this compound, 0.25 moles of this compound, has 0.25 moles of Cr, 0.75 moles of Cl, 1 mole of N, and 3 moles of H. Another type of question we might see is how many oxide ions, or O2-, are there in 2 moles of Fe2O3? Step 1. Calculate the number of moles of oxide ions present. There are 2 moles of Fe2O3, and there are 3 moles of oxide ions per mole of Fe2O3. Because there are 3 oxide ions per compound, therefore there are 3 moles of oxide ions per mole of the compound. We multiply 2 by 3, and we get 6 moles of oxide ions present. Step 2. Convert to number of ions. Now, as we've said before, if we have a number of moles of elements, ions, or molecules, we can simply multiply that amount of moles of ions, or elements, or molecules by Avogadro's number, 6.022 times 10 to the 23rd. We can multiply the moles of given oxide ions, or molecules, or elements of anything by 6.022 times 10 to the 23rd, which is Avogadro's number, to get the number of ions, or elements, or molecules. In this case, we're multiplying 6 moles of ions, and we get 3.613 times 10 to the 24th oxide ions.